Hey class, we are still in chapter 2 and we'll be looking at literal equations and dimensional analysis. So let's check out our vocabulary today. We have literal equation, and that's a formula or equation that involves two or more variables. And I want to specify that that would be different variables. So here's an example of one that you might have. E equals mc squared. Here we have a formula that has three different variables. The next one is dimensional analysis or unit analysis. So both words refer to the same concept. And this is something you guys have done before. It's the process of carrying units throughout a computation. So when we're going from meters to kilometers, or from inches to feet to yards to miles, that's when you'd use dimensional analysis. So the real thing about literal equations that you need to keep in mind is the fact that when you do problems and you're solving, you will not get a numerical answer. You will get an answer in terms of one of the variables. For example, in example 1, we're asked to solve for a specific variable. In this case, it says solve this equation for the variable m. What we will do is focus our attention on m. I'm going to rewrite this equation, and I'm going to highlight this m, which is what I want to focus on. So I want to find a way to get m by itself. So what I will do is leave the m term on this side and get rid of everything else that is not an m term. So really we can consider putting our m terms over here, and instead of putting just constants on the other side, we'll put everything else. All right, so with that in mind, let's get started. To get rid of this minus 3n, I'm going to have to add 3n to both sides. So I'm adding the additive inverse or the opposite. So I'm now left with 4m is equal to 3n plus 8. Still, m is not alone. 4 is being multiplied next to m. The opposite of multiplication is division. What I do to one side, I do to the other. And my answer is as follows. My answer is exactly what you see here, 3n plus 8. 3n plus 8 divided by 4. That's what m is equal to. I hope example 1 was pretty straightforward. Example 2 is going to take a little bit more work and a little bit more thinking. We're solving for x, which is fine, but we see that x is in two places. It's here and it's also here. So we're going to have to join like terms together that don't seem alike. So we're going to talk about some interesting things. Let me rewrite this. Okay, so as we look at this problem, it does seem a little bit more complicated because we've got an x term here and then this x term here that has is it an x term, is it a z term? Since we're solving for x, we're going to call this an x term, and we're going to move our x terms over here, and on the other side of the equal sign, I'm going to put an e for everything else, all right? So when I do this, I realize that the 2y needs to get going, so I'm going to add 2y to both sides. Once I do that, I'm left with 3x is equal to xz plus the 2y plus the 5. Where I place these, by the way, it doesn't matter. I could have put plus 2y plus 5, then plus xz. I could change the order. As we know, addition is, we've got the commutative property of addition, so things could move around. All right, so with that in mind, now I need to move this guy. I got to get the xz out of here because this is an x term. So I'm going to add the opposite to both sides, and when I do that, it's like subtracting. So I get 3x minus xz is equal to 2y plus 5. So I needed to kind of scooch this up a little bit. So here's the ending part where we were. So I need to join these guys together. So I'm going to put a little thought bubble down here and think about, what do I usually do? If this were something like 3x minus, I don't know, minus 2x, what would we do? We would just go 3 minus 2, right? And then have the x over here. 3 minus 2 is 1. My answer would be 1x, or simply just x. Another thought bubble. What if I had any kind of situation? What if I had like 3x plus 5? What would I do? 5x, pardon me. I would take the 3 and the 5, add those together, and then give it an x, let it be an x term, pardon me, and I would get 8x. So what all of this evidence is pointing to is the simple fact that we're going to have to do something kind of interesting. What this is looking like to me, I don't know if you guys are checking it out, but in my thought bubbles, what I'm seeing is something that looks like the reverse distributive property. Can you see that? It's like I'm pulling the x out and leaving everything else in there. And that's what we're going to call it now. Later we'll call it factoring, but right now we're kind of doing something neat like the reverse distributive property. So what I've done is if you notice there's an x here and an x here, I've pulled it out, I've left it on the outside, so I know that if I needed to, I could multiply it back in. Same thing on this particular thought. So let's go back to our problem, use that information to help us simplify our situation. Back to the problem, you can see that we've got the x terms on one side, which is what we want, and everything else on the other. So now it's time for me to manipulate this side. What we saw in our thought bubble is that x can kind of come out. Since I've got x here and x here, I could actually write this as 3 minus z, right, times x. Because recall, if I wanted to, I could distribute it back in, and it would be exactly what we have at the top. But that's not what I want to do. I want x separated from all of that mess so I can isolate it. Remember, we're still trying to solve for x. So now that x is by itself, I see x is being multiplied by 3 minus z. Therefore, I'm going to divide this side and the entire other side by 3 minus z. When I do that, I see that x is equal to 2y plus 5, all of that over 3 minus z. And I'm feeling pretty good about myself, as you should be too if you followed that along. If you followed along with that. If you did not and it was a little bit complicated, go back and check the thought bubble. See if you can make up examples like that on your own and see if you can see the natural follow through of what we're going to call the reverse distributive property. In example 3 here, we're going to see how we can actually use literal equations. In part A, it talks about the circumference of a circle being given by the formula c equals 2 pi r. And you guys should remember that circumference is equal to 2 times pi times r. Some teachers might have taught you circumference is equal to pi times d. Well, d being the diameter, 2r does equal d, so it really is equivalent. All right. So r is the radius of the circle. We're going to solve this formula for r, which is not too bad. So if I have c equals 2 pi r, I need to get r by herself. And to do that, circle it, focus on that, I need to just get rid of everything else. R needs to be on this side of the equation, and everything else needs to be on the other side. And so now that I've kind of established that, the 2 pi is the obvious candidate to be divided away, because 2 pi is being multiplied by r. When I do that, I get the equation. I'm going to put a line here. R is simply equal to c, the circumference, divided by 2 pi. And as many pi days as we've had, you might remember seeing some kind of work around circles and circumference and how it all relates together. All right, the largest yo-yo in the world has a circumference of 32.7 feet. What is the radius of this very large yo-yo? So here we can use the work that we did in part A to answer this question in part B. The beautiful thing is that we've now solved the equation such that we can get the radius r right away by knowing the circumference. So what we'll do is we'll take c, replace it with 32.7 because that is the circumference of the largest yo-yo in the world. And then we'll divide it by 2 pi. When we do that, we get approximately 5.2 feet, which we know is important to say feet because we started off talking about feet. So units are important. We want to hold on to that. Example 4 requires us to use a concept called dimensional analysis. In this problem, we're going to be considering a 10K or 10 kilometer long run. And then we want to figure out what that length of a run is in terms of miles. We're given some unit transfer information. We know that 1 meter is equal to 1.094 yards and 1 mile is equal to 1,760 yards. So we're going to use that information to our benefit and we're going to we're going to figure out the answer to this. So we'll start off with 10 kilometers. And what we want to do is see if maybe we can turn our kilometers into meters, because meters and kilometers are obviously related. And we can then, once we get it in terms of meters, we can get them into yards. So to do that, I need to find out what the unit relationship is between kilometers and meters. Since I want to turn this into meters, I know my meters will go up at the top and my kilometers will go at the bottom. How many meters are in a kilometer? I think most of you know that that's 1,000 to 1. So when I change, and I'm going to put km here as well to be consistent, when I change from these 10 kilometers to meters, I'm going to have to multiply 10 by 1,000. And then so at the end of this part of the problem, I'm going to get 10,000 meters. The next thing I'm going to do, because now I'm at meters, and let me write this in another color. So now I'm just going to put it up here, 10,000 meters. Now I want to change these meters into yards, and I have a wonderful relationship here. It says 1 meter is equal to 1.09 yards up here. So I want yards, so yards will go at the top, and I'm going to put 1.094, and at the bottom I'll put 1 meter. So what's going to happen is my meters cancel out, and I will get this new value in yards. And of course, that brings me the 10,940 yards. Now that we're in yards, we're going to move to miles, because we've got a unit relationship. 1 mile is to 1,760 yards. So can you guess what I'm going to put at the top since I want to change it into miles? Yes, miles. So I'm going to put MILES here. 1 goes at the top, and 1,760 yards go at the bottom. And then so when I finally multiply this, you'll see that the kilometers changed to meters, the meters then canceled out and I got yards, and then finally I'm going to cancel out my yards by continuing this problem, and then I'll get the miles value, which is approximately 6.2 miles. So at the end of the day, we know that 10 kilometers is equal to a 10 kilometer run is equal to a 6.2 mile run. Now for our assignment. All right, guys, our assignment is as follows: pages 129 to 130, 9 through 21 odd, and then 24 through 26, 29, 30, 37, and 39. Have an excellent day. Look forward to seeing you guys soon.